Hello, good afternoon. This is Rafael Capilla speaking. This paper is the result of a collaboration between different universities from 3 different countries, and where we study the impact of opportunistic reuse practices related to technical debt. One of the things I would like to highlight is that compared to traditional approaches where companies try to adopt a systematic reuse approach, today it is very common to have opportunistic reuse practices where reusable assets can be found in open source repositories like GitHub, GitLab, and SourceForge, among others. So nowadays, several studies try to quantify this reusability index or the level of reuse, but to the best of our knowledge, there are no studies showing the connection between opportunistic reuse practices and technical debt. Therefore, the main motivation for this paper is the lack of very few studies showing the impact in software architecture when we try to reuse open source components and describing or reporting the connection between reusable assets found opportunistically and technical debt, and also how the selection of the right open source components has different implications in the system or in the architecture. Hence, we try to analyze this aspect in depth and which are the effects in the software architecture and technical debt ratios when we try to reuse assets opportunistically from open source repositories. Consequently, the main goals of this work is to try to understand the relationships between opportunistic reuse and technical debt and try to analyze with more depth the effects in architectural debt when we reuse assets opportunistically, and also investigate the effects in technical debt ratios, the number of smells, the number of issues that can be detected using two different tools, SonarQube and Arcan, when we reuse assets and we integrate these assets found opportunistically into an existing system. In order to cover the proposed goals, we came up with the following research questions. So the first research question is about which are the most difficult aspects to integrate new functionality found opportunistically in open source projects. So we study here the effort and the changes required by a developer when has to integrate third-party components. In the second research question, we analyze how code debt is affected after the integration of reusable assets found opportunistically. So here we wanted to investigate to what extent opportunistic reuse practices have a significant impact on technical debt ratios and the number of smells in the code. Finally, our third research question is about how architectural debt is affected by reusing open source software. So basically, we are interested to analyze how this architectural debt or how the architecture is affected when new components are introduced in the existing architecture. In order to answer the research questions, we use as case study 3 different sample systems. So the first one is a bicycle hiring system, a small Java system developed at the Technical University of Madrid. The second one, Teammates, is a much bigger project. It's an open source project used for the peer evaluation of students' team projects. And finally, the third one is Kurki, a Finnish system used to manage the participation of the students in courses. In order to reuse components opportunistically, we use 4 different repositories: Maven, GitHub, SourceForge, and GitLab, and 2 different tools, one commercial tool, SonarQube, and one research tool, Arcan. So we use SonarQube to analyze the number of technical debt ratios, number of smells, and issues in the 3 systems, and we use Arcan to detect the architectural smells, the architectural debt index, and the quantification of this index. And we compute all the numbers before and after reusing the components opportunistically. In this slide, we can see the functionality reused or found for each of the projects in the different repositories. So the first table shows the number of components we found in these repositories. For instance, for the first application for bike app, we add a component to encode the data, a facility to geolocate the bicycles, or a calendar system. So here in this table, we can see the number of components found in these repositories. However, in the table below, we can see the components selected according to the different criteria for each of the sample systems. In the case of BIAP, for encoding the data, we select two different repositories, Maven and Sourceforge, to reuse the base64 component, and so on for the rest of the systems. Here we describe the results for the three research questions. So regarding the first one, which are the most difficult aspects to integrate new functionality found opportunistically, we summarize below some of the reasons. So for instance, we had to analyze the functionality and the compatibility of the new component and understand if it serves and it can be integrated in the system. If the reused component has dependencies to third-party libraries, if we need to create new classes to invoke the component because this affects the integration effort, or if the architectural style of the reused component is compatible with the architectural style of the existing system. So in the table we can see the numbers regarding the search effort and in the right part the integration effort. So in many cases, the search effort was higher than the integration effort because we need to find the components, or we found the component in different repositories, and we need to select which of these components is more suitable according to different criteria. In the case of Kurki, we can see that the search effort for the full calendar or event manager system is 0 because was the same one as the one we reused for the teammates project. Here we show the results regarding research question 2, how code depth is affected after the integration of reusable assets. So in the upper table, we can see the results using SonarQube, describing the technical depth ratios, the number of smells and issues for the three projects before reuse. And in the table below, we can see the same ratios after reuse. As we can observe, for the first and third project, the technical depth ratios decrease, mainly due because of the size of the reused components and because SonarQube takes into account the number of lines of code. And Teammates is a bigger project, so the technical depth ratio remain almost the same after reuse. However, the number of smells and the number of issues in the three projects increase once we reuse and integrate the components. Finally, we provide here the result for research question 3, how architectural depth is affected by reusing open source software. So in the first table, we can see the result provided by the Arcan tool, showing the number of architectural smells, architectural depth index, and the quantification of the index for the three different projects. And in the table below, we see the same ratios computed after reuse. So for Kurki, which exhibits the best results, the ratios remain the same, but we only reuse one component, and the worst results belong to Bicap and Teammates. In the case of Teammates, we have the same number of architectural smells, but even the architectural smells remain the same. The depth increased because it worsened in terms of severity. And the worst results belong to Bicap because it increased the number of architectural smells and also the architectural depth index. Another result of our work is to estimate which was the impact in the design or in the architecture after reusing the components. So here we can observe the architecture of the first system, of the Bicap system, before reusing the new functionalities. So we display in pink color the client server classes and in gray color the Java archive files. So once we reuse the functionality of the three components, these are highlighted in green color, but also new components that we have to create to invoke this functionality. While in yellow, we can see additional components that were required to reuse the new assets. Finally, the findings derived from our work is that we observe that the technical depth decreases if large components are reused, but in the case of small components, the technical depth ratio tends to remain almost the same. Cyclic dependency was the most common smell we found using Arcan and SonarQube tools, and the architectural depth increases after reuse, mainly when we reuse big components or large-scale components. Finally, we need to carry out additional integration efforts when the architectural styles of the existing system and the reused components is not the same. But in our case, to avoid these additional integration efforts, we try to reuse components that have similar architectural styles. As future work, we plan to investigate not only additional technical debt ratios or number of smells, but also try to investigate the quality and severity of new smells after reuse. And we also plan to carry out more experiments with more components and how to fix the architectural mismatch when we reuse a component that has a different architectural style compared to the architecture of the existing system. And also we can compare our results from our Java projects with other assets reused in other programming languages. All in all, although our results are not conclusive about predicting these technical debt ratios and number of smells, in our opinion, opens a new research path to measure better which are the effects of opportunistic reuse practices in existing systems and in the architecture as well. So this is our presentation. So thank you very much and open for questions.
Hello, sorry for the delay. We had the final question in the previous presentation. So the next presentation comes from Rafael Capilla, and the presentation is on the impact of opportunistic reuse on technical debt. So Rafa, the floor is yours.
Okay, thank you very much. Good afternoon. So this paper is a collaboration between 5 different universities, and we will talk about we study the impact of opportunistic reuse practices related to technical debt. So for many years, traditionally, systematic reuse approaches have been adopted by software companies to reuse software components or even use a different kind of proprietary forms of software reuse. But today, because of the popularity of open source repositories like GitHub, GitLab, SourceForge, and many more others, the trend, or one of the major trends, is to try to reuse software components from third-party developers in an opportunistic way or in an ad hoc manner. So today, we found that several studies try to quantify this level of reusability or this level of reuse or computer reusability index, but few of these works try to show the connection between software reuse and technical debt. So mainly the motivation of this work was based because there are only few studies showing the impact in the software architecture when developers try to reuse open source components, or they try to explain which is the connection between technical debt and opportunistic reuse, and also because the reuse and selection of open source components developed by third-party developers can have several or strong implications in the target system and in the architecture as well. Consequently, we wanted to analyze in more depth which are the effects in the software architecture and in the technical debt ratios when we try to reuse assets opportunistically from all these variety and plethora of repositories. So we came up with several goals for this research work. The first thing is we try to understand much better which is the relationship, if any, between opportunistic reuse practices and technical debt. Also analyze with more depth which are the effects in the architectural and in the architectural debt indexes when we reuse assets opportunistically.
but also try to investigate the effects in the technical dev ratios, the number of smells, the number of issues that can be detected by these popular tools. Like, for instance, in this work, we use the commercial tool SonarCube, and also a research tool developed at the University of Milano-Bicocca, which is Arcan, to compute the architectural depth index of software. So we came up with the 3 research questions looking for this evidence. The first one is, which are the most difficult aspects when we try to integrate these reusable assets found opportunistically into an existing system, and also try to compute the search efforts finding these assets and estimate the integration efforts of these assets into an existing system. Also, the second research question is about how the code depth is affected, or it can be affected after the integration of the reusable assets that can be found opportunistically, how these ratios or technical depth ratios vary before and after reuse. And finally, our third research question is how the architecture, the software architecture, is affected when we reuse the asset, and also how the architectural depth that can be estimated like tools like Arcan is impacted when we reuse this asset opportunistically. So to provide the evidence for this study, we used 3 different projects. The first one was developed at the Technical University of Madrid. It's a small Java project about a bicycle hiring system. The second one is an open source project. It makes a much bigger project used for the peer evaluation of student team projects. And finally, the third one is an old software project, a Finnish system, Carrillo, that uses to manage the participation of the students in courses. So for about the repositories, we decide according to different criteria used in the following 4 repositories: Maven, GitHub, SurfOrg, and GitLab. And we use the SonarCube 8.5 version of this tool and Arcan to estimate the technical depth ratios, the number of smells, and the architectural depth index, and also, of course, also the number of the architectural smells and the architectural depth index of the projects. And we compute all these numbers before and after reuse to compare the different results. So, excuse me. So, okay. So first we see here 2 tables. The upper table shows or displays the number of reusable assets found opportunistically. As we can see in some of the repositories, there are many. So we decide to have some brainstorming to add some new functionality to these projects. So for instance, in the case of the bike app system, we agree to incorporate an encoding system between the client and the server, or display geolocation of the bike's facility and a calendar. And for the teammates, we add a voting system and an event manager. And for the last one, we also add an event manager to compare the technical depth ratios between teammates and Carrillo. So the first table shows the number of components using Google queries that were refined afterwards in the repositories. And the table below shows the components, the specific components we found or we select among the many components found previously for each different functionality in each of the software projects. For instance, for the encoding the data, we found base 64 components in SurfOrg and Maven. But for instance, in our case, we selected, according to this, to the criteria, the component from SurfOrg because no dependencies were required. But in the case of the Google Maps, we selected or we reused it from Maven because it provides some compatibility information with the existing system. The results, answering the results for the 3 research questions. So for the first one, which were the most difficult aspects to integrate the functionality or the new functionality that we found opportunistically. So we analyzed different aspects, in particular the functionality of the new components and its compatibility with the existing system, and if we can fit the reused component into the existing system, and also if they have or they don't have dependencies to external libraries, or if we need to spend effort creating new classes to invoke the component. And also very important was to check the architectural style of the different components. So in some cases, because due to technology or the platform uses or the architectural style of the reused component, we found differences between these architectural styles of the existing systems and the reused components. So this was an important decision point or decision criterion to select a particular component from a repository. And the table shows the search and integration effort of the reused asset. As we can see, we spent significant time in the search effort because we found many components and we have to, according to the different criteria indicated in the paper, select a component from a particular repository. We don't have search effort for Carrillo for the full calendar because it's the same component. And after we saw here in the right column, the integration effort, according to all these aspects we have mentioned before, if they have dependencies or compatible licenses or documentation explaining how the component works, or depending of the reused component, we spend different integration efforts. About the result of research question 2, how the code depth was affected after the integration, we saw first in the upper table the results computed before the reuse. So we, using the SonarQube tool, we compute the technical depth ratios and the number of smells and the number of issues. And the table below show the same or similar numbers after reuse. So in the case of Bicap and Carrillo, the technical depth ratios decrease, but this is very dependent of the size of the reused component, because for large component, how SonarQube computes the technical depth ratios depends on the number of the source lines of code. So this is why the technical depth ratios decrease. But in all cases, if we go to the details, the number of smells and the number of issues increase. In the case for the results of research question 3, how the architectural depth was or is affected or it can be impacted by reusing the open source software. In this case, we use the Arcan tool to compute the number of architectural smells and the architectural depth index before and after. And in the case, in the results after reuse, we can see that the numbers remains for Carrillo, but we only reuse one component here. For teammates, we have the same number of architectural smells, but the severity and the criticality of these smells increase as the architectural depth index show in the table. And for Bicap, we got the worst results. Another outcome that we investigate from our work was which were the changes in the architectures. So here we can show an excerpt or part of the architecture of the Bicap. So even it's difficult to appreciate the details, so we can see in pink color the client-server classes and in gray color the Java archive files. And after reuse, we can see some of the changes in the architecture. So the green color are the classes that we had to add to the for invoking the new functionality. And in yellow color, we can see new libraries that were required when we add some of the components. For instance, when we add the Google Maps services for the geolocation of the bikes, we had to include all these components here. So overall, we had to modify an additional 70% of the architecture to add the 3 new components for the Bicap. So finally, our findings of this work is that in general, we observe that the technical depth ratios decrease when large components are reused, but for small components, the technical depth ratios remain almost the same. Cyclic dependency was one of the most common smells found in the projects. And also in general, architectural depth tend to increase after reuse when the reused components are big. And also, in some cases, especially for the BICAP project, we need to spend some additional integration efforts and some refactorings to fit the components into the architecture, because in some cases, we detect that the components that we have found in different repositories, they vary according to the technology used, so they have a different architectural style, and this is very important because we have to fit both architectural styles, or find a component with a similar architectural style to avoid major refactorings in the software architecture. So as future work, we plan to investigate much more the quality and the severity of the new smells regarding the architectural depth index. Of course, we need to carry much more experiments to validate our approach and try to figure out how to fix the issues when we have different architectural styles between the reused component and the existing architecture. We can also compare our results as a replica experiment with assets written in other programming languages. And it will be also interesting to provide guidelines for developers to select much faster and more accurate the components to reuse in order to reduce the search efforts. This is something that I have observed, in particular in my university, in developers working in European projects, that they are reusing many times components in open source repositories, and they spend a lot of time to select and to decide about which is the best software component to reuse. So this is why we want to provide them some guidelines to make the selection much faster and more accurate according to different criteria. So thank you very much. This is my presentation, so I'm open for questions.
Thanks a lot, Rafa, for a very interesting presentation.
Thank you.
We have a question from the audience, from Wesley, so I start from that. The question seeks for alternatives to opportunistic reuse and specifically software product lines. And he asks if you have any clue on such cases and how they impact technical.
Yeah, well, we are not focusing in our approach in any specific development approach like software product lines, or in particular destructive model. We just try to find reusable software or third-party software in open source repositories, but I think it's not tied to the development approach. Use it like a software product line. Perhaps when we fix the technical debt, agile can impact. But for reusing, I think the problems are to find components with similar architectural styles and don't spend much effort or much time finding these repositories. But to be honest, we didn't try with these extractive models from software product line, but it will be interesting to try something or to have some experience in the future. Thank you.
Thank you. Since there is no other question in the chat, of course, feel free to add more. I have a question of my own. So one of the things that were always in my mind when thinking of reuse and software quality and how they relate is not comparing the quality of the code that is brought in the system, but how the system needs to change in order to get the new component in the source code, and how this changes change the quality. So how is the surrounding quality of the new code is modified? So when I add a new library, I change the source code of the target application. So does this improve or reduce quality?
Well, this is a very interesting question because it's not very easy to answer, because sometimes what we observe is that the technical debt ratios remain the same. So if they remain the same, why should I fix this technical debt? But if we go to the details, analyzing the specific smells and the quality of the smells and the severity of the smells and the distribution of the smells along the history of the project, is not so easy to provide an answer how to fix the quality of the system after reuse, because we have to take a very careful look to the type and the severity of the smells. So I think this is not, doesn't have an easy answer, but at least can provide some guidelines or some clues to where to look in your code. But the most problematic thing that we found is that reusing components with different architectural styles. So this is one of the most complicated things.
Indeed, finding a match between the target and the source architecture is a key thing while reusing, and
that's true.
We have also seen it a lot in our research. Is there any other question from the audience? Okay, one very, since we have less than a minute, so very quickly, I suppose that the components that you have incorporated into the code were reused in a white box manner, right? So you brought the whole code inside with the binary.
Yes, white box, but we have to take a look for compatibility, for dependencies to external components or libraries, if they have appropriate, suitable documentation to understand the component, and it can be fitted and provide guidelines or Java documents to explain how to fit and use the components. So there are, in the paper, we list 5, 6, 7 criteria that developers can check to know how to fit a component and what they have to look for.
Thank you, Rafa. Since 10 seconds are left, maybe you can continue the discussion offline since there's another question from Wesley. Thanks a lot.
Yeah, thank you.